Now a little theoretical summary of what we've been doing with all of that dividing and factoring. So, the first one is that when you divide a polynomial by some divisor and get a quotient and a remainder of degree smaller than the degree of the divisor, well, there's only one way to do that. It might never have entered your mind that there was more than one way to do that. For that matter, that there was more than one way to do something with natural numbers and division. We know that there's only one remainder that we're going to get when we divide 35 by 8 because of how division works. Well, this is just a statement of how division works that is a useful theoretical foundation for what's going to come. Okay, next one. Suppose that we take a polynomial f of x and divide it by x minus c. Whatever that constant term c is, here, the remainder of the polynomial is going to be f of c. In other words, the polynomial evaluated right there. This fact turns out to have some rather profound results. Like what? Well, okay, we're given that when we divide that we're going to get that remainder. Suppose we go back to that 7th degree polynomial that we were dividing a little while ago, and we are asked, what is f of negative 2? Okay, well, what would you rather do? Put a negative 2 through all of this with all the potential for error that there is there, or synthetic division, which we saw was very simple compared. Okay, so that fact is actually called the remainder theorem. And we have cases of special interest, and that is when the remainder is 0. That means if we have a remainder of 0, then we know that this value is a real 0 of the polynomial. And zeros of polynomial are always going to be of interest to us, particularly in calculus. In our study in pre-calc, we need to know where a polynomial is positive or negative. In calculus, that amounts to telling us where these vertices are, because the derivative function that you'll learn to find in calculus, its zeros are going to give you the turning points of the function whose derivative it is. Sounds a little funky now, but believe me, if you learn how to find these zeros now, it's going to have a big payoff when you get to calculus. Okay, so coming from this, we have this fact that once you have the polynomial and the constant, if the function evaluated at that constant is 0, then we are given right there one of the factors of the polynomial. And it works the other way around. If we know that whatever it is a factor, then we have found a 0. This is called the factor theorem. Again, so what? Well, let us suppose that you are given a polynomial and you are asked to find its factors. There's always a question like this on the final. Last semester, there was one student in the whole class who graphed it, who said, oh, I see it hits the horizontal axis at this place and that place and the other place. I have my zeros, therefore I have my factors, I'm done. The entire rest of the class must have spent 10 minutes dividing this, dividing that, which was not necessary. And you're not going to have 10 minutes in calculus to do that. You need to know this fact that you can graph it, and presto, find the zeros just that easily. Notice that while these are the zeros, I don't know what scale it is until I evaluate the function a little more closely, but that's easy to do. I just find the value of the y-intercept. Every polynomial has one, if you think about it. And I'm done. So, remember, if you need to factor a polynomial, the very first thing to do is to graph it. This is one way in which your study of mathematics is different from mine. You have a calculator to do that graphing with. Here's one example from the book. We're given an equation, this polynomial is equal to 0, and we're given a partial graph. Well, what do we know already? We see that the degree of the polynomial is 3, therefore we know it has 3 real zeros. Or no, I shouldn't say that, not 3 real zeros. It has 3 zeros, and at least one of them is this real zero. The scale is given in this illustration in the book, that x equals -3 is one of them. How do I find the others? I'm going to do division by x plus 3. You can use long division if you want, or you can use synthetic division, which generally goes a lot faster and more easily. There we are. So this part here gives us the second degree polynomial, or quadratic. That is the quotient when the divisor is x plus 3. So we can rewrite the left-hand side as the product of these two factors. Now, we found 1 0, we still have 2 to go, and we can factor that quadratic on the right using any method that pleases us. Eyeball, quadratic formula, complete the square. I chose, in this case, to try to factor it without doing any of those other methods, and I was successful in finding such a factorization. Notice this 2 here. Well, if I factor that out, then I get the scale. So here, if we wrote 2x minus 1 is equal to 0, we would have to do that factoring out of the 2 at some point to arrive at the fact that 1/2 is the 0 that we need there. So here's where it goes, right up front. And observe, this 2 is the same as this 2, the leading coefficient of the polynomial to begin with. That will always be the case. That really simplifies things.